Thank you. Okay, so we'll start with just an extremely simple introduction to what biochar is. So up here we've got roughly 8 petagrams of carbon anthropogenic emissions going into the atmosphere every year. Most mitigation strategies seek to reduce that. Like Beck's, biochar seeks to look at this much larger flow through the biosphere. In this case, by converting some of this biomass into a product which is very much more stable and returns its carbon to the atmosphere much more slowly than raw biomass would do. Biochar is essentially charcoal or black carbon produced by pyrolysis, which means heating the biomass in the absence of oxygen. Now, obviously, this kind of approach is going to be very dependent on just how stable that charcoal is in the environment, and particularly in soils where we're thinking of putting it. Before we look at exactly how stable biochar is, it's worth taking a look at how stable we really need it to be. So up on the top right there, we've got a graph looking at net avoided emissions over a 100-year timescale, and looking at its sensitivity to different half-lives. And what we can see is that, provided the half-life of the biochar is greater than around 200 years, there's very little difference in terms of its net sequestration over 100 years, whereas you've got a very sharp drop-off for shorter half-lives below 100. However, if we think about longer timescales, if we want to think about sequestration over, say, 500 years, here we can say that we really need to have biochar half-lives at least in excess of 500 years before we're without getting a large drop-off in the net sequestration over that sort of timescale. So just how stable is biochar? That's pretty much like asking how long is a piece of string? It really all depends on how you make it. Pyrolysis intensity we've got here really corresponds to increasing temperatures, increasing residence times and reaction times. Sometimes higher pressures are used as well, but less so. And the more intense your pyrolysis conditions, you move gradually from a raw biomass state towards something which approaches the structure of graphite, with a whole range of different structures in between. Along that process, you're gradually reducing the oxygen content of the material, the hydrogen content, increasing its 3D order as well. So if you look at the literature to try and understand just how stable it is in soil environments, we've got estimates of the half-life of biochar in soils ranging from tens of years to, well, 10 to the 7s of years. We've got 6 orders of magnitude of variation in the estimates out there. Now, that was all we knew about it. You'd say, put up your hands up and say, we really don't know anything about how stable this is. But in fact, a lot of this variation, some of this variation is real uncertainty because there are very large methodological issues with trying to estimate decay rates over very long time periods. If you do it in incubations in the lab, you've only got a very short time period to extrapolate from. If you look at soils, you know very, very little about how much biochar has been in them long term. So there's a certain amount of uncertainty just from that. But a lot of this variation is also due to how much you've moved the pyrolysis process towards the sort of graphitic nature of the biochar. So here we've got plotted the oxygen-carbon ratio of the biochar against its half-life, and there's some sort of correlation here. Now we can see to get a OC ratio of below 0.2, we can pretty much guarantee that the pyrolysis temperature is about 500 degrees or higher, and that will give us half-lives at least in the 1,000-year timescales or greater, which is certainly what we need for sort of half-millennium sequestration. So it's very practical to achieve that kind of stability. So we're thinking about putting biochar into soils. We need to be very clear about what the risks and benefits of doing so are, soils being one of the most valuable things we have, along with air and water. Now, it's quite important to understand that black carbon is not an alien component to soils. It's ubiquitous. It occurs everywhere in all soils around the world, and it's generally the oldest and most stable fraction of soil carbon. If you plot it sort of on a geographic basis, you see it peaks around the more arid zones of the sort of plus and minus 20 degrees latitude. Also, it's very interesting that some of the soils with the highest black carbon contents tend to be some of the most fertile ones, including things like mollisols, which you have here in the US a lot. And very interestingly, some of the anthrasols, black earths, which really initially started off the interest in this topic. We've got here a very well-known picture looking at some of the black earths in the Amazon, comparing an adjacent soil, which has not been converted using biochar historically, with very poorly fertile soils, compared to the pockets of terra preta adjacent to them, where you get very fertile soils. And this is really what initially drove the interest in biochar as a sequestration mechanism. If you look at how much carbon is in these soils, and also the benefits of fertility, it starts to look very attractive. When we take the same model and try and do it in short-term pot and field trials, the results are not quite as astounding, but there's a large variation, and most of the trials that have been done to date show a net increase in yield of crops. Anything from, well, the lower end, you've got a sort of 5% increase up to 40% increase on average. You've got some cases where you've got negative impacts on yields. Now, if you look at the mechanisms for these, they tend to be due to improved nutrient cycling or improved water retention. In order to get increases in yields, you need to be getting some sort of impact on something that's causing a constraint on fertility. So most of these studies have been done on soils that are inherently quite infertile, and these are the easiest ones to address particular pH or water or nutrient constraints. Where we've got negative impacts on yield, that's generally because people have done things like adding a very alkaline biochar to a soil that's already very alkaline, which is going to reduce your production, or indeed adding biochar to very clayey soils, thereby reducing the water retention. So we know, but there's a lot of potential for creating different types of biochar with different properties to address different soil constraints. So it's very important to produce the right material for the right place. This graph really is just emphasizing the point that the impacts that we'll get on the most fertile soils, this is a chronosequence looking at soils converted from forest. So the shortest time since conversion, you've got the highest fertility. Over time, soil carbon is depleted and you get more and more degraded soils. So here we've got, on the most degraded soils, you get very good positive impacts from biochar. On the most fertile soils, you get very little impact or even possibly a slight suppression of yield. Now, biochar is not the only product you get when you pyrolyze biomass. The interesting thing from this meeting is also the energy production potential. So here on the top left, we've got a graph showing that as you increase the temperature, you're going to reduce your yield of char, and instead of getting so much char, you're increasing your product of volatiles and gases, which in turn can be combusted to provide energy. Now, this penalty of reduced char as you increase the temperature does not necessarily transfer into a reduction in the sequestered carbon long term, because as you increase the temperature, you end up with a more stable form of carbon. And if we look here at the fixed carbon content, it's pretty flat over a wide temperature range, allowing you a lot of potential to optimize the process for energy production rather than just your initial biochar yield if you're interested in the sequestration potential. So just how much energy could you get out of this? Well, this is a study looking at a few different mechanisms or pathways for converting biomass to co-production of biochar and liquid fuels, or transport fuels, I should say. It's not comprehensive, but it covers some of the more interesting pathways here. You start off with about 19 gigajoules per ton of in your raw biomass on average. That's on an ash-free basis anyway. And if we vary the pyrolysis temperature here, we can get different yields of biochar. So each of these lines is a pathway as we vary the pyrolysis temperature. You'll see here for this, we're getting reduced yields of biochar. And once you get to about 700 degrees, you start to get tar cracking and far more gas produced, which increases the amount of energy you can get out from the useful syngas, carbon monoxide and hydrogen-rich syngases. Alternatively, these vertical bars here show what happens if you take some of the liquid tar products and have a tar cracking unit to convert them as well into syngas. That way we can get away with higher yields of biochar and lower temperatures, which are quite important for the kind of materials you can use in the conversion process and the costs of the capital cost. And with a tar cracking unit, you can get similar yields of energy with higher amounts of biochar. Once you look at the losses required for actually driving the pyrolysis process and heat losses and parasitic losses in the process, from that initial 19 gigajoules, you'll end up with about 7 or 8 remaining in the biochar, which is essentially squandered from an energy point of view, but useful from a sequestration point of view. And you can end up with about 7 gigajoules of useful energy at the end of that process. So one of the burning questions for me when I first started looking at biochar was, can it actually realistically be scaled up to actually deal with global emissions in a useful amount? So other people have spoken about the fact that all biomass utilization has the same issues in terms of where you get your feedstock from. It can be have a net positive or net negative effects on the sustainability of the system. So what I've tried to do here is to limit these feedstock supply scenarios to within what can be achieved without using more residues than you can take out without causing soil erosion or soil degradation. Now, a lot of time people think about agricultural residues, for example, as being a free resource that could be used for bioenergy. It's very important to bear in mind the important functions they have if they're returned to the soil. If you take too much out, you're going to degrade your soils and you're going to end up with far more abandoned and useless cropland and starving people. So you absolutely need to think about how much retention you need to keep in your soils in order to maintain long-term fertility. Now, obviously, you need to think about not having large debts, carbon debts from land use change or conversion of currently wild habitat. No use of contaminated waste, because we're looking at a product here which is slightly different to burning in a power station, where if your ash is contaminated, you dispose of it as a waste product. Here we've got something that's going back into the food production system, so we can't use municipal waste products that are going to have, for example, heavy metal product in them. The conversion technology is very important. Charcoal was historically made in kilns which produced very large emissions of VOCs, methane, soot, and other noxious things, and also they have very low efficiency of conversion to biochar, and they have zero efficiency of conversion to energy. So we need to use modern technology that addresses those problems. So within these 3 scenarios, which are constrained by within these, we can get maybe a maximum of 1 to 2 petagrams of carbon per year feedstock carbon, which translates into a maximum abatement potential of about 1 to 1.6 petagrams per year from the biochar itself. Now, at these very high utilization rates, which are assuming that you've got very large scale up to the maximum potential by about mid-century, if you did that, you're going to start reaching your maximum amount of biochar that you can add to soils before they might harm fertility. Within the sort of later half of the century at the highest utilization rates. That's not necessarily an upper cap on what you can do. You can then think about putting it deeper into soils, below the plough layer. You can think about using other soils, such as pasture and forestry soils, or other disposal methods beyond that. So looking at the breakdown of where these avoided emissions come from, now on the right-hand side of these charts, we've got 2 columns, one for biochar here, and another one to compare it to of just using the same biomass, but combusting it for maximum energy production to offset fossil fuels. So the largest abatement comes from this actual sequestration of the carbon you store in the soils. There's also a substantial component from avoided fossil fuel use from the energy production. In both cases, bioenergy and biochar, there's quite a lot of avoided methane emissions from paddy rice fields if you take that straw that would otherwise create methane in the fields and do something else with it. Nitrous oxide emissions can also be reduced quite substantially by biochar. And the main negative feedbacks are from the biochar decomposition itself, and also from diverting biomass away from soils, you're going to lose some of your initial soil carbon. Now, those are just very average values for the whole globe. If we start looking in a little bit more detail about regional variations, there's actually a lot of deviation from those averages. So these charts plot here on the x-axis, we've got the carbon intensity of the fuel system that you're actually offsetting with your energy production. And here we're looking at the local soils with the most infertile soils at the top there, which can receive the most benefit from biochar, and the most fertile soils at the bottom, which really don't get any noticeable increase in yield from biochar, but they may have improved fertilizer use and water use. The x's mark the sort of global average spot, which was what we saw in the previous graphs. But we can see that here that we can go from the average up to very large increases in terms of the abatement potential of biochar. If you put them in locations which have traditionally used a lot of biomass fuel, for example, so in places where wood is a large component of the fuel and you're not offsetting much fossil fuels, and you've got very infertile soils, you can get a very much better performance from biochar than bioenergy. Conversely, if you move to regions where you've got a very coal-intense economy and you've got very fertile soils, the American Midwest comes to mind as an example there, then it looks like bioenergy is going to be a better option there. So far we've looked at just comparing bioenergy and biochar on a per unit feedstock basis. However, that's not really the limiting factor in terms of biomass availability is amount of land you've got available rather than the amount of feedstock. So what we've got here, we're looking at something called priming, whereby biochar can have very profound effects on the cycling of soil organic carbon. So if you look at these graphs here, the orange bars down here show what happens to your soil carbon. If you simply remove your residues and convert it to bioenergy, you get a gradual depletion of soil carbon and gradual degradation. And that's really the limiting factor on how much agricultural residues you can take out and use for bioenergy. You need to put at least 75% in most circumstances. It varies depending on latitude and climate. But you need to put a substantial part of your residues back into the soil if you want to maintain soil fertility. However, if you take that same amount of biomass and convert it to biochar, which goes back into the soil, there are some positive feedbacks between the cycling of soil organic carbon, and you allow soils to store more carbon and stabilize carbon more efficiently once they've got biochar in. You can actually remove biomass and this is a 100-year timescale, end up building soil carbon rather than depleting it. Now, that's very important if we put it in context of how much residues we can extract sustainably from a field. So here we've got a hectare of corn. This is one example, with about 8 tons per hectare. This is based on American values. It varies a lot worldwide. 8 tons of residues in that field produced every year. If you're going down the bioenergy route, you can maybe take at most 25% of that out. You get quite a good conversion efficiency. This is based on syngas to methanol conversion rates. Obviously, the technology used will be very important here. You might end up with about 30 gigajoules at the end of that. On the other hand, if you're going to be putting biochar back into the soil, you can remove a very much larger proportion of the initial residues while still maintaining soil fertility. And although a smaller fraction of your residues will be converted to energy, because you've got this very much larger amount of residues available, you can maintain similar amounts of energy production per hectare of land to bioenergy, while at the same time producing biochar. So here we're starting to look at a sort of a first preliminary look at the relative economics of the two approaches. This is really a very simple model comparing bioenergy and biochar, so the net costs minus the benefits of either one of the approaches. And these different lines refer to different soil fertility. So on the black line here, we've got the very fertile soils, where you see that over time, you've got the net benefit of using biochar rather than bioenergy, it always remains negative. Whereas over time, with your more infertile soils, the benefits of increased yields over time accumulate, and they offset some of the initial higher costs of biochar relative to bioenergy. And after 25 plus years, depending on the fertility of your initial soil, you'll end up in the black or in the net benefit from using biochar rather than bioenergy. It's a very long payback time, but it's, I think we're in the game of looking at long time scales once we're talking about climate anyway. Now, of course, the economics are very dependent on a number of factors, and very importantly, the type of feedstock you use here. This is a study which was done looking at biochar systems in the UK, and here we see that of the net costs and benefits of producing biochar, the feedstock cost is one of the most important things. So there's a few examples where if you're taking waste products that would have a fee attached to them, actually for you to take them off instead of dumping it in a landfill, you can end up have a negative cost if you're making a biochar. Whereas depending on the feedstock source, the cost of production can rise rapidly. So this is a sort of just a first stab at trying to put this in the context of a global scale. This is quite a familiar graph probably to some of you. It's from a paper by Enquist. It's what's called a marginal abatement cost curve. So it plots on the x-axis here the total abatement potential of each of these different technologies, and against the lifetime cost of actually implementing those technologies. Now, some of these technologies here, over their lifetime, will save you more money than the cost to do in the first place, particularly efficiency measures. So they'll have a net. So you've got a certain amount of abatement potential at a net negative cost over time. Once you move up into the positive ones, you've got, well, I mean, these numbers are very debatable, and I would take them all with a pinch of salt. There's large uncertainties attached to all of them. But we've got moving from things like nuclear up here to putting CCS on industrial processes up at the top end there. So as a first sort of guess at where biochar might fit in that, we've got estimates that have been produced saying that the cost of producing biochar is going to be somewhere in the region of 21 to 30 euros per tonne. And from the sustainability assessment I showed earlier, we've got the total abatement potential of 3.7 to 6.6 gigatons. So that puts it somewhere within these error bars here on this global scale. Certainly not the most expensive and certainly not the cheapest option for abatement, but one with quite a large abatement potential anyway. So in conclusion, we can see that we can certainly engineer biochar to produce something which is sufficiently stable, and we can control its properties to suit different soil conditions. Typically, so far, short-term field trials have shown benefits to crop yields. There's a complete absence so far of any field trials of more than 3 to 4 years, so we know very little about how biochar performs over the medium-long term. There's cause for some optimism about how it might perform in the long term from anthrasols, which typically have very high fertility compared to the adjacent soils. On average, the mitigation potential from biochar looks like it should be better than bioenergy alone. Obviously, I haven't compared it to bioenergy with CCS. That's another important question to look at later. But there's large regional variations in that. As I said, if you want to do it in places with very infertile soils and low carbon intense economics, it looks very good. In places which are very carbon intense and rich soils, it doesn't look so good. The short-term economics certainly would favour bioenergy over biochar. However, in the long term of 25 years plus, you start to see some real benefits from the improved crop yields that can offset some of that. Carbon credits, so I skipped over that graph, but carbon credits really have almost no impact on the relative economics of biochar and bioenergy because their mitigation potential is broadly similar. So even at very high carbon credits of up to, say, $200 per tonne, you see very little change to the relative economics of bioenergy versus biochar. And so we need to compare it to a lot more different types of options, including BECCS. And so I can't read my last one there. I was considered just, okay, it's really important when you're really looking at anything to do with biomass that assessments are not just done on the mitigation potential, and they're not just done on the pure economics, but you have to look at the wider sustainability issues. And of paramount importance in anything that utilises biomass is its effect on soil And yeah, okay, and soil degradation. Okay, thank you. I'll take any questions.
Thanks. We have time for one or two quick questions. Right in the back, and then we'll get to Larry.
Yes, relating to your last point, Brian von Herzen from the Climate Foundation. When you do the biochar processing on agricultural residues, it's common for the nitrate to be converted to nitrogen, perhaps, which could result in a loss of nitrate for the soils. Could you comment on approaches that might address sustainability in the context of nitrate and other macronutrients?
Yeah, sure. Yeah, pyrolysis does convert at least 80% of your of the nitrogen that's in the feedstock into nitrogen. It depends what you're using as a feedstock. It really doesn't look very good to use high nitrogen feedstocks such as manures, whereas if you're using more lignocellulosic biomass, they tend to be very low in nitrogen anyway, so the penalty is not so high. Also, your nitrogen use efficiency, once you've got the biochar in the soils, is improved. So if you're looking at low nitrogen content fuels with an improved nitrogen use efficiency thereafter, you end up with a net benefit after 5 to 10 years in terms of nitrogen production. There is an initial loss, though. There are other potential things which have been looked at, which is, for example, using the biochar before, rather than dumping it straight into the soil after you've used it. You can use, it's a extremely good adsorbent for particularly cations such as ammonium, but it also seems to absorb nitrate. So you can use it to scavenge nutrients which are otherwise being lost, for example, from livestock production units or from sewage works and other things like that. So you can use it to scavenge and recoup some of those losses and transfer them back to the soil with actually a net gain in nitrogen rather than a net loss.
Have you looked, so most of your comparisons were biochar versus bioenergy.
Yeah.
But in a world where biomass is the limited resource, does it make sense to do a comparison of biochar versus using that char as a fuel and displacing an equivalent amount of coal or some other CO2 fossil fuel?
Yeah.
And how does that analysis turn out?
Well, I think that's broadly similar to this, to the same. If you pyrolyze it to produce syngas and biochar or charcoal, and then you combust both the syngas and the charcoal, the efficiencies are not drastically different to simply combusting the biomass in the first place. So overall, that comes to a very similar picture to what I've shown there for pure simple combustion.